I will begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class and these students. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So today, I will explain to you guys a little bit about what is special relativity. And I'm going to take a somewhat high-level approach to this. So I won't be deriving much of anything. Relativity, yes. So like the heart of special relativity rests on Einstein's axioms, right? And Einstein has two axioms. The one axiom is that the speed of light should be the same in all frames of reference. And the other is that the laws of physics should be written in the same way in all frames of reference. So there's no preferred reference frame. And that's usually something along those lines is what's given as Einstein's axioms. But there's really more to it than that. There's also an assumption that physics reduces to what we already know at low velocities. When you study the derivation of what are known as Lorentz transformations, you'll see that at some point or another they use the assumption that at the limit of low velocities we return to what we already know, like in basic physics, right? So there is a certain naturalness that's also assumed. There's also a reversal symmetry that there's an interchange symmetry, like if I'm going past somebody on a train, right, then they see me going past in the opposite way, right? There's this V and minus V exchange symmetry. And if you study the derivation of the Lorentz transformations, it uses all of those things, all right? Maybe I'll even show you guys that next time. It depends on where things go. But at the end of the day, we learned that we should study space-time. And so space-time, we use x upper 0 equals to ct. X upper 1 equals to x, let's say, and x upper 2 equals to y, x upper 3 equals to z, right? These are space-time coordinates measured with respect to a fixed inertial frame of reference. And don't ask me how you find those, how you measure those, how you set up that inertial observer. You'd have to ask a real physicist for that, right? People write pages and pages to try to describe. But suppose you had one, right? An inertial frame of reference like this. You could use, for instance, the frame of reference defined by the fixed background stars. Usually people say something like that. That gives you an unmoving frame, right? But you notice that time has been thrown into the mix as another coordinate, right? And that is a vast departure from classical mechanics, where time stands alone, aloof, over in the corner, and it just parametrizes everything. Absolute, universal, Newtonian time. Now time has a seat at the table where all the other coordinates are listed, right? And so this is space-time measured with respect to one inertial observer. With respect to another inertial observer, we might use bars. X bar naught, X bar 1, X bar 2, X bar 3. And you can derive then that for two inertially related observers, well, not this, excuse me, I should say, this is a particular example of it, but you do gamma times x upper 0 minus beta x1, gamma times x upper 1 minus beta x upper 0, and this one's just x2, and this one's just x3. These are called, this transformation I've just written is known as a Lorentz transformation, all right? It's a very particular one based on what I would call an X boost. right? So like pictorially, it's something like this. You've got, you know, your fixed frame, right? And you've got your moving frame, let's say S bar. And here's the x-axis, here's the x-bar axis, right? And you're moving with velocity v that way, all right? Now here, specifically, gamma is 1 over the square root of 1 minus v squared over c squared, which we could also write as 1 over the square root of 1 minus beta squared, right? And here beta is the velocity divided by c, right? Now these formulas, right? And this, you can derive these formulas from the axioms that I just mentioned, all right? Like it's relatively easy to do it. I show physics 231 this, all right? But you notice that already baked into the cake here, if your velocity was like larger than c, you see what happens to that formula. Yeah, you got to use your imagination, right? So, yeah, so we see that the speed limit is already built into these Lorentz transformations, which is not surprising in some sense. But, all right, great. Now, notice that like the top equation, just to make sure that, let me make contact with your previous course just for a second here. So like we have CT bar, right, is equal to gamma times CT minus V over C times X, right? And if you solve this, you got T bar is like, you know, gamma times T minus Vx divided by C squared, right? That's probably what you saw in the previous course for the Lorentz transformation formula for time, right? Because you probably didn't work with CT in the previous course. And if you look at the x1 equation, that gives us x bar is gamma times x minus, what is beta? Well, that's V over C, right, times CT, which of course is gamma times x minus VT. And there you go, that's the standard Lorentz transformation, you know, not using space-time coordinates, but just using time and space, yeah, without the C. You notice what happens when the velocity is 0, gamma is 1, and we're just back to x bar is equal to x minus VT. So, you know, that's how these would, and so we're really relating things on like the x-axis at the moment, or something like that. All right, enough. So, I want to point out to you guys that we can write that as x bar, let me write over here. All right, so we got x bar naught, x bar 1, x bar 2, x bar 3, times this particular matrix, which is what? Gamma minus gamma beta, gamma beta, gamma. 1 and 1, zeros down here, zeros up there. Right, it's this 4 by 4 matrix. This matrix that I'm writing is called a Lorentz matrix. All right. Typical notation is that this is lambda. All right. So the first story arc I'm working on here, guys, is trying to describe to you what a 4 vector is. We're trying to come to terms with, like, what are the basic rules for the playground in which we're playing. And the rules are that physically interesting things have to be described as 4 vectors, at least to start with a 4 vector. What's a 4 vector? Well, to start with, the space-time position is a 4 vector. Like this is a 4 vector. Be more explicit here. We can write x upper mu is equal to the sum. All right, now I got to be careful. Nu equals 0 to 3 of lambda, lower nu, upper mu, x upper nu. And of course I got bars over here. This is the Lorentz transformation in a, explicit coordinate way. Now, you could also do, here's another formula you might see. You might see this like x bar mu prime is equal to like lambda mu prime nu x nu. This uses Einstein's summation convention. A repeated index is summed over. All right. So far, so good. And so, in this wild world of interesting notation, you also write things like, there's some other things we could work out, like partial x bar mu prime, partial x, let's say, I don't know, I need another letter here, alpha is equal to partial x alpha of, we just wrote that down, right? Just trying to show you some calculations here, just to get our feet wet. X nu, x upper nu, right? All right, so this is, by the way, constant. The Lorentz transformation doesn't depend on where you are in space-time. It just depends on the velocity, right, of the boost. So, and that's a fixed velocity. We're assuming that the inertial frames of reference are related with respect to a fixed and constant velocity, all right? So that means this pulls out, right? And you're just left with like lambda mu prime nu, partial x nu, partial x alpha. Now, if you remember your calculus 3, this is just Kronecker delta alpha nu, right? And as such, this simplifies to lambda mu prime alpha. So if you wanted, you could rewrite the Lorentz transformations in terms of partial derivatives of the coordinates. Okay, but another thing maybe you remember from previous calculus, maybe not, whatever. But if I had like partial mu prime, partial x alpha, partial x alpha, partial x bar, I don't know, nu prime, let's say, what should that be equal to? 1, right. So by the chain rule, this is the chain rule, this is partial x bar mu prime, partial x nu prime, which would be Kronecker delta mu prime nu prime. So, but on the flip side, this is also lambda, let's see here, mu prime alpha, lambda, apparently alpha nu prime equals to Kronecker mu prime nu prime. To put it into words, this and this are like inverse transformations, which kind of makes sense if you think about it, right? Notice that I'm using primes on the indices to denote the choice of frame. This is a kind of sneaky notation. So like, I could write x mu prime, x mu, x upper mu as lambda upper mu lower nu prime x bar nu prime. Like, you compare and contrast these formulas, right? transferring from the unbarred to the barred versus transferring from the barred to the unbarred. These are inverse transformations. All right? Okay, so just a little bit on that notation, yeah? All right. What's probably more important is the following. So, definition, G as a matrix, let's say mu nu. Write this as to express it as a matrix, and the way this is going to work is it's -1 and then 1's down the diagonal. So another way we could write this is G mu nu is like Kronecker 0 mu Kronecker 0 nu with a minus plus Kronecker, listen to me, 1 mu Kronecker 1 nu plus Kronecker 2 mu Kronecker 2 nu Kronecker 3 mu Kronecker 3 nu. If you wanted to, you could do it like that. There's a stone cold formula for, well, this has a name. This is called the Minkowski metric. So here's a definition. Given, let's say, a bar, which is equal to a upper mu. All right. So I'm just sorry for this litany of notation, but it's important for us to have a few different ways to process these things. All right. So this is a 4-vector, a contravariant 4-vector. Contravariant because the index is up. I can also express this as like a upper 0, and it's just the vector part. Notice that I'm using bar and vector dissimilarly. I use vector for a 3-vector, I use bar for a 4-vector. Likewise for B, all right, we define the Minkowski product, and I don't think this is in Stewart, guys. I mean, it is, but it isn't, all right? I'm adding some things to Stewart here for sure. You mean Griffiths? Oh, Stewart, listen to me. I interchange Stewart and Griffiths. I've got a Stewart-Griffiths, like, interchange in my mind somehow. I don't know how it happened, but it's not polite to either one of them, I guess, but. Or is that impolite to both of them, now that I say that? I don't know. I mean, I like both of their books in a way. But, I mean, Griffiths, of course, has been invaluable to us this semester. If nothing else, I've been just talking to Griffiths the whole semester, right? So, I mean, you got to start somewhere. And I do think Griffiths is a good place to start. All right, so the Minkowski product of 4 vectors A and B is this. It's A bar dot B bar, let's say. And that's going to be minus A0, B0 plus A1, B1 plus A2, B2 plus A3, B3, all right? We can express that in terms of ordinary garden variety, like Calc 3 dot products, as what? Like minus A0, B0 plus what? Plus the dot product of the vector parts of A and B, right? Like that? You guys see that, right? And then we can also use the matrix G. I can write it like this. I can write it like A bar transpose times the G matrix times B bar, like that. Where here I'm taking the viewpoint that I'm taking the viewpoint that A bar is technically an element of R4 by 1 in terms of linear algebra. It's a column vector. So when I transpose it, I've got row vector times matrix times column vector. Yeah, so that's the Minkowski product. In terms of the repeated index notation, that looks like G mu nu, A upper mu, B upper nu, which is pretty beautiful. Don't you think? It's pretty clean.
That'd be A dot B sub mu is equal to that?
No.
Oh, wait, no. Sorry, it's just A.
No, so matrix notation, repeated index summation notation. There is yet another thing to enter the scene, raising and lowering indices. So A sub lower mu is defined to be G mu nu A upper nu. So this is how we lower the index on A upper mu, right? These are the so-called here A0, A1, A2, A3, right? These things are the so-called covariant components of A. Covariant components. So look over here. See what we could do? I could rewrite this as like A upper mu, G mu nu, B nu, right? Look at this right here. That's nothing more than B sub mu. So we have A upper mu, B lower mu. And that is another way to express the Minkowski 4 product. All right. So I've showed you a particular instance of a Lorentz transformation, right? This X boost. But there's more than that. All right? There's more than that. And so we can define, right? We can define Lorentz transformations in terms of the interaction of a transformation with the Minkowski product. And so and I suppose there's probably something, well, I gotta be careful. I may be like assuming, I'm trying to think about something. I really only want to think about linear transformations. In the abstract, you might think about affine transformations, and there would be more to say here. Like, if you think about Euclidean motions in the plane, there are different kinds of Euclidean motions in the plane. There's like rotations, reflections, but there's also translations. And I'm not interested in like the translational issue here. I just want to think about sort of the analog of rotations here. If you think about rotations and translations with respect to space-time, that brings you to like space-time translations, which are interesting, I think. But that's not what I'm trying to talk about at the moment. I just want to focus on like Lorentz transformations. And so, so definition, given like linear map on R4, right, such that, you know, like, I don't know, for lack of imagination, t of x equals to x bar, all right? So here I'm so in matrix notation, x bar is equal to lambda x, okay? And here I'm talking about the 4 vectors, right? So like x is equal to x, or x upper mu that we've been talking about. I guess I owe you guys some of my current notation. Ah, no, the bar has got me now. Son of a gun. It's finally dawned on me. I'm not using this bar as a change of coordinates. I'm using this to signify 4 vector. Ooh. Rats. I need to pay the piper at some point here. Do you guys see what I'm saying? I did not, just to be clear, I'm using bar here to indicate 4 vector. I'm not trying to indicate A and B in another coordinate system. I don't know. I don't want to give up on the 4 vector notation just yet. And I don't want to give up on the bars for other coordinate systems just yet. I guess we're just going to have to deal with it from context, yeah? Sorry about that. As I said, you can blame the math club. So, it's for a good cause, though. What's that? Use an underline. Yeah, that's something else. Yeah. Okay, so anyway, if we say T is a Lorentz transformation, if let's see here, T of x dot T of y is equal to x dot y for all events x and y in R4. Oh, by the way, a time and a place is an event. So we're talking about how to transform events. Well, at least to start with, I mean, we do abstract this to think about, in the same way we do in okay, so you think about this. In Physics 231, we talk about vectors as displacement, right? But are vectors always displacements? No, they're soon forces, momentum, velocity, they're other things, right? Same with 4 vector. Start with thinking about it in terms of an event, but it will soon think about it in terms of for momentum, for velocity, for force, and other things. But we got to start somewhere. So I start with events. Okay, so listen, this then becomes what? This is the Minkowski product. So what we're looking at is lambda times x transposed times my Minkowski metric g, right, times lambda times y is equal to, well, x transpose times g times y. All right, but then you guys know linear algebra, right?
I'm taking a 5.
More than enough. You know the sock shoes identity, right? So the transpose of a product is product of transposes in inverse order? Sock shoes identity? Yes, no? Maybe so? Let me do it. Let me do it. So x transpose, lambda transpose, g lambda y is equal to x. I should have made this a homework. Oh man. Oh well, too late. So that condition has to hold for all x and y. But if a matrix identity holds for all rows on the one side and all columns on the other, you just take the rows and the columns to be the standard basis and you can get the arbitrary components have to be equal. It follows that we need lambda transpose g lambda equal to g again. And this right here defines lambda a Lorentz matrix. So a Lorentz matrix, more generally, satisfies this condition. That's a particular example of a Lorentz matrix, but there are many others.
That being that?
Yeah. Like that, you could try, will solve this equation. It will. Now, let me foolishly attempt, well, maybe I should save that for homework. Tell you what, I'm going to save this one for homework. This is probably a good exercise to put this all together. So a good exercise is this. All right? Show that x bar mu prime x bar mu prime is equal to x mu x mu. Where x bar mu prime is lambda mu prime nu x nu, and x bar lower mu prime is lambda lower mu prime upper, nu x nu. So this is something I make myself work through whenever I'm doing this material. So see if you can work that out. I think I've given you all the necessary ingredients to do it here today so far. All right, so in a nutshell, a 4-vector in special relativity is a vector, a 4-dimensional vector, which transforms in the same way as coordinates. So like, this is definition, A upper mu is a contravariant 4-vector provided that A mu prime, I guess I ought to use the bar, I'm sorry guys. I guess it's clear enough. If there's an index, then we're talking about coordinate change, right? So x bar mu prime is lambda mu prime nu A sub A upper nu, yeah. That's a contravariant 4-vector. In other words, A transforms under coordinate change in the same way that coordinates do, right? A contravariant 4-vector transforms the same way that a coordinate does. And you can also define a covariant 4-vector. Let me use a B. B lower mu is a covariant 4-vector provided that B lower mu bar prime is lambda, let's say mu prime nu B lower nu. So I'm saying that they transform inversely. Another good exercise A bar oh man, A bar mu prime, A bar mu prime, oh my, rats. Wait a minute. Let me put the B. I don't think I need the same letter. Man, I'm rusty. B mu prime is equal to A mu B mu. In other words, this is the kind of calculational principle we need to write equations of physics according to Einstein's axioms. Because what I'm saying is if I form the Minkowski four-product between A and B in the barred frame of reference, then that four-product is also equal to the same thing in the unbarred frame of reference. See, so if I formulate laws of physics in terms of these kinds of expressions, then that is in good agreement with Einstein's axiom. The laws of physics have to have the same form in different inertial frames of reference. So,
Here, what is bar versus prime?
bar. It's a doubly, like I'm using bar to indicate it's in the prime. I'm using primes for the indices of the barred objects. But they're both together with the moving frame. Let's say if let's say that the unadorned frame is the fixed frame, then the bar or the prime is the moving frame. Yeah. Admittedly, everything's always moving, right? Because you'd be like, well, no, the unbarred frame is actually also moving because if you take the perspective of the primed frame, it's moving with the opposite direction. True. All right. So, all right. Sorry, I'm trying to find something. Where'd it go? Where'd it go to? Well, rats. Can't find it. Trying to make sure, I gotta make sure I've got my conventions right. I don't dare go off memory. I'll mess something up, you know? All right. So, theorem. A upper mu equal to V over C, comma, AX, AY, AZ is a four vector called the four vector potential. And so like A lower mu, what would that be? If we, when you lower the indices, what does it do? Like think about how the G works. It doesn't do anything. If you sort through it, it doesn't do anything to the spatial indices. It just puts a minus on the temporal term. So like when you sort through the definition I wrote, this just becomes minus V over C, and then the same, these guys just ride along. So it's actually true that that is a 4 vector. If I define it, and here I mean V is the potential and A is the vector potential. I'm talking about the voltage and the vector potential from this semester. Yeah, exactly. And so then you can use this, all right, to define the field tensor F mu nu as equal to partial A nu partial X mu, oopsie, oh well, yeah, it is. X mu minus partial A mu partial X nu in Griffith's notation. Now, this right here is what's called a tensor. Well, this is the field tensor. And so like if I did F bar mu nu, I guess I got primes, right? That would be partial A bar nu prime partial X bar mu prime minus partial A bar mu prime partial X bar nu prime, I suppose, right? And my claim is that's actually equal to lambda mu prime mu, lambda nu prime nu, F lower, excuse me, F upper mu nu. I guess I should clarify. This is what it means for it to be a tensor with 2 indices. So this is how a tensor with 2 indices has to transform. We need 2 lambdas. Some physicists will call this a rank 2 tensor. Yeah.
Does this suppose that lambda commutes with those derivatives? In other words, that it's not dependent on?
Yeah, this is only for Lorentz transformations. Lambda is a Lorentz transformation, not a general coordinate transformation. I mean, you're right. If we're talking about transformation of coordinates which depends on position, then it's not this simple. That's a much harder problem. That's general relativity. That's what that is. So, I don't know, I wanted to show you guys an example of a 4 vector today. And in fact, this, if you can take derivatives of the 4 vector in this way, as it turns out, and that creates something called the field tensor, which again is, well, it's tensorial. And we can actually write Maxwell's equations using the field tensor. We'll see that the field tensor has the electric and the magnetic fields in it. Let me use the projector for a bit here. I have some things I should show you. So a proper treatment of this material doesn't, I've jumped to the end at the beginning, all right? This is horrible. This is truly horrible what I've just done. Like, this is like, you know, you start watching The Matrix, right? And then like somebody's like, just so you know, this isn't the real world and he's actually plugged in like a battery. You know, like 2 minutes into the movie, something like that. You know, it wouldn't be, I'm sorry, did I ruin The Matrix for you? I mean, but, no, it's okay. It's rated R, I know we don't watch that here. But, what's that? Still watching. I saw it in the theater when it came out. It was amazing. Like it was such a, I mean, yeah, I mean, movies before that versus after that, just totally. It's too bad the creators of that movie kind of, anyway. Yeah. I had such high expectations for like the sequels. It never really lived up. I really want, anyway, I'll shut up. I had like very meta ideas about where it was going and it just didn't flesh out. All right. So I have a bunch of stuff written up from when I taught general relativity. And I think it's helpful for us to just kind of like look through some of those and talk things through a bit. So in these notes, I'm using eta rather than G. A lot of people use eta instead of G, and they use G for the more general thing. Like eta is the specific Minkowski metric, whereas G is like a possibly point-dependent metric. Yeah? So there's that. Now, so if you look at two events and look at the displacement between those, right? The Minkowski product of that displacement with itself is called the interval. The interval between two events is an invariant. It's the same if you measure it with respect to two different reference frames. So you can work problems like you might have worked in your time in that course, where you compare events in a moving frame versus a fixed frame, and you can use this to solve a variety of, interesting, weird things that involve the fact that this difference and sum of squares is equal if you compare a moving and a fixed frame. Now, so as I talked to you guys mostly today about four vectors, here they are. All right, great. One of the things, I say metric, but in the sense of mathematics, it's not a metric in the sense of an inner product because there are null vectors. There are non-zero vectors that the Minkowski product is zero. That means this is well outside the scope of most mathematicians who only think about positive definite inner products. Linear algebra gets much nastier when there's null vectors for the metric. Space-time diagrams are super helpful. We can draw pictures, at least two-dimensionally, to kind of picture what's going on, space, time, upwards. And light rays, 45 degrees, right? If you're above the light ray, you've got a time-like motion. Below the light rays, space-like motion. Basically, things inside the so-called light cone, right, are things that you can physically reach through real trajectories of material particles from the origin there. And everything outside, below, or like over here in like C, that corresponds to faster than light travel, right? So sometimes people call everything to the left and to the right the present. This is the past. That's the future, above the light cone. All right. So this I don't think matters to us today. Let me go on here. If I could tell which one I'm on, that would be wonderful. Index calculation. Oof. So you guys have suffered through my index calculation at the start of this semester, but there it is again. Great. Let's move on. Isometries of Minkowski space. This is what I'm just talking about. It's, we say it's a isometry of Minkowski space if basically the Minkowski product is preserved between events. So as I was mentioning, space-time translations also preserve the interval between events. I'm not being very precise. I'm sorry. If it weighs on me too much, I will. Oh, come on. Listen, I just started you at the end. I wanted to start you at the beginning. I'm a dummy. I was on page 6. Page 1. So we have a space-time finally, good grief. Space-time translation, we add both to time and to space. A space-time translation. A Lorentz transformation is what we study today for most part, right? It's like a rotation, generalized rotation. It could be a boost, but actually rotations are involved. And so that might be a solution to the exercise. Don't look too much at that. But of course, like the space-time translation is kind of dumb, right? If you add a 4-vector and add a 4-vector to both, and you take the difference, of course, they cancel, and you have that. And the invariant interval is equal, provided that the matrix which rotates in the Lorentz sense satisfies this identity, right? Which is what it takes for it to be a Lorentz transformation, as I was just describing. All right. So the Lorentz transformations, which you can also denote O31, are the set of all 4x4 matrices that satisfy that lovely identity at the top. And there's a bunch of stuff in there that we don't really care too much about. I mean, physicists care. It's got these parity transformations, right? Those are kind of inversions around the different spatial axes. And it's got this thing here. What's that do? What's that transformation do? Hit time-space with this, what happens? If you make a mistake in your life, you'd like to use that. You gotta know, take you back in time. That's time reversal right there. See, because it changed t bar is minus t, right? So this is the funny thing, is equations of physics oftentimes have time reversal symmetry. What does that mean? Well, you can read the pages about it in Griffiths, come to your own conclusions if physicists understand. I have my own feelings. I don't understand. Then again, I told you I'm not a physicist, so there you go. All right, anyway, if you specialize to the subset of the Lorentz matrices, which has determinant 1, and it has the 0, 0 component greater than or equal to 1, this is called the proper orthochronous Lorentz group. Those are the ones that actually correspond to real physical Lorentz transformations in the way we typically think of time, the arrow of time being preserved, stuff like that, all right? So here's some examples. Don't look too hard at these. These have answers to homework problems I intend to assign to you. Like one of the homework problems in Griffiths? Yes, Griffiths, I remembered. So, is to rewrite the matrix that I've covered up with the whiteboard right now, I mean the projector screen, as this. If you rewrite gamma in terms of the rapidity is defined to be, rapidity is a cool thing. It's hyperbolic tangent of the rapidity is equal to beta. And if you study this, well, I'm not going to ruin it. You guys study it. You see what you find out. I had to learn it for myself, so you should too. But anyway, in terms of the rapidity, you can write the Lorentz transformations in terms of rapidity. This is the x boost. This is a y boost, I think. This is a z boost in terms of rapidity. Other examples of Lorentz transformations are simply rotations. The garden variety, just rotations around an axis in 3 dimensions, do nothing with time. Those are also Lorentz transformations. Because you guys know from Dr. Budaras' class, well, that classical mechanics has rotational symmetry in the basic equations, right? That has to still be present in the theory of special relativity. Indeed it is. In fact, there's kind of 2 halves, in some sense, to the Lorentz group. There's the rotational half and the boost half. They're all intertwined, but that's kind of, it's all there. Okay. Enough about that. Next. So 4 vectors in physics. I've talked to you guys a little about this. We'll talk about proper time and all that next time. I'm not going to hurry through proper time. But basically, the long story short of it is by using proper time to formulate velocity and acceleration and everything, it all works together nicely, and we get a way to find a basically, if you differentiate your position with respect to proper time, it gives you a 4-vector, which means then we can write down equations with it in the 4-vector sense. If we differentiate the position with respect to ordinary time, right, we don't get a 4-vector, and it would be much more complicated from that perspective. Now, the notation Griffith uses for proper velocity is eta. I dislike this notation immensely. The common notation for proper velocity is u, like this. A big U, capital U for proper velocity. And then ordinary velocity measured with respect to the fixed inertial frame is little u. This is all for the trajectory of a moving particle. So there's, right, and anyway, so like the 4 velocity has 2 pieces. It's got gamma c and gamma u, where this is the ordinary velocity. So this is also, this part of it is sometimes called the relativistic velocity. Relativistic velocity is gamma times the ordinary velocity. And this right here is something new. And I'm going to do all this next time again. I just want to run through it real quick with you guys. For acceleration is like the second derivative with respect to proper time of your space-time position. All right. And you can learn that it's related to the ordinary acceleration in this rather complicated way. All right. And there are cool theorems like the proper velocity and the proper acceleration are Minkowski orthogonal. Whatever that means. And then down here, come on, I'll show you something. Here's the velocity transformation rules. For momentum is defined to be like the rest mass times the proper velocity. And so like momentum has 2 pieces. It's got m gamma c and m gamma u. So that's sometimes the spatial component there is called relativistic momentum, which is just gamma times the ordinary momentum, right? Or you could say mass times the relativistic velocity is the relativistic momentum. I don't work with relativistic mass. Mass is a constant called the rest mass. In the older literature, sometimes they talk about mass as a variable. I never do this. Mass is always constant. And if you expand m gamma c squared, which is the 0th component in the 4 momentum, that gives you mc squared plus this. So the 0th component is actually the energy, which has 2 pieces, the rest energy, which is rather famous, and here is the kinetic energy, which you've studied more. So now, the acceleration you can work out has 2 pieces in terms of the force applied. It's got this piece and that piece. So if the force is like perpendicular to the velocity, this is 0, like it would be for circular motion. This is that gamma I was talking about for the circular motion. Like acceleration times gamma is actually the force divided by m naught. That's that gamma I was talking about in the cyclotron motion that I missed in my qualifying exam. There it is. And here's the relativistic derivation of cyclotron motion, right? All right, great. Well, eventually, I want to talk to you guys about classical field theory because you'd like to see this. This right here, guys, is the right there, E and M and Lagrangian formulation. That I know you guys want to see that, right? There it is. And oopsie, now we're into linear algebra. Oh man. Well, anyway, so my goal after break is to give you a lecture where I just give you a nice, clean, tidy presentation of like 4 momentum and talk to you about how we can solve like collision problems using 4 vectors, because I think that's of interest, right? And then the next lecture should just be on, like the field tensor and how the electric and magnetic fields change when we change from frames of reference, because the fact that the